All right, so we're back talking about section 1.2, the reading problems, the applications of linear equations, and we were just getting ready to talk about the distance problems. So distance problems have a root formula that distance d is always equal to the rate times time. And if you think about it, if there was only one vehicle involved, and say d equals rt is the base formula, if you were driving 60 miles an hour, that's a rate, times 2 hours, you will get 120 miles. These two always multiply to equal this one. So that's the base formula idea we use for all distance problems. In these distance problems, though, we're going to have two vehicles. Trains, planes, and automobiles, whatever vehicles are involved, they'll either be going towards each other, away from each other, or various scenarios that we've got here. So it helps if you draw a chart. So usually whenever you see traditionally in a math book a distance problem, you see a chart emerge for a lot of these things we're going to do. And it's because there's two or more things going on at the same time, and it helps us organize our thoughts. So in my chart, I've got a distance equals rate times time formula maybe across the top. And you can put that in the reverse order, rate times time equals distance. I think maybe they do that in your book, so I don't want that to bother you. But it could be in either direction, because equality means this side's equal to that side. And you'll have two vehicles. In this case, they're steamboats, I believe. Let's see, let's read this. At a given hour, two steamboats leave a city in the same direction on a straight canal. Again, I like these little pictures. And I don't know what a steamboat actually looks like. Maybe sort of steam there. Okay, but the steamboat is going down the canal, and then another steamboat, there's some steam, going down the canal. So they're both going in the same direction, right? It said that, same direction on a straight canal. One travels 18 miles per hour. You know, they're not speedy. So one's going 18 miles per hour and the other one's going 25 miles per hour. And they left at the same time, it says. And the question is, in how many hours will the boats be 35 miles apart? You know, this one's going faster. And I've seen students just draw that out and figure it out by hand, which is kind of cool. You could figure that out if you thought about it for a little while, how long, you know, what happens every maybe 5 minutes or every hour in this. I think this one comes out nice and even, so you could figure it out with maybe just drawing the picture, and I embrace however you figure it out. But the concept is this one's getting ahead of this one, and the question is, when is this distance between them going to be 35 miles? When does it pull 35 miles ahead of the other one? I want to do it, though, the traditional chart method. I'm going to say I've got steamboat 1 and 2, or however you want to label it or not. And 35 is not the distance traveled by either one of these steamboats, by the way. I know it's tempting to put the 35 in for D, but it's the distance between them. We'll use that in the equation writing process. What we do know a lot about is the rate. That's the most obvious probably here. So putting the two rates down. And then we really don't know anything about the time exactly. That's our basic unknown here. How long does it take this to happen? What we do know is it was at the same time at a given hour they started, and that this happens. They've been on the canal consistently. So we don't know the time, but we know it's the same. So if we can express, and this one they could have said 1 hour longer or 2 hours less. They could have made it, you know, some factor there for us to use, but it was exactly the same. Whatever time this one's exactly the same. Then we can use the formula idea that rate times time will equal distance. So that's how we'll fill in this part, 18 times t, or 18t, and 25t. And then we'll use what we know from our picture to decipher what to do with these two distances. And what we want to do is actually subtract. When will this distance minus this distance leave a difference, you know, of 35? So we want to put the equation is 25t minus 18t equals the 35 miles between them. So that's 7t equals 35, divide by 7, and the answer did come out nice and neat. It doesn't always, but this came out to be 5 hours. 35 over 7, t is 5. And you could sort of check it out. You could say 18 times 5, see what that is, 25 times 5, and see that it kind of works out in your drawing. All right, so that's that idea. The next one, And always feel free to pause the video and try these before I explain them, so that might be a better strategy. I'm going to go ahead though, but I know that you can pause. We're talking about Lexington and Ashland. Say you're driving, let's say, suppose you leave Lexington traveling an average speed of 60 miles per hour east towards Ashland. So you leave, say here's Lexington, you're driving that way in your car, and at the same time your friend leaves Ashland. So here's your friend in Ashland driving towards Lexington west at an average of 65 miles an hour. So in their car, 65 miles an hour over here, and you're driving at 60 miles an hour there. Assuming the total distance between Ashland and Lexington is 125 miles, how long until you will pass one another? All right, so you're going along. This one's a little bit slower, so you're not going to pass exactly in the middle. That'd be too easy, right? But at some point, you're going to pass on the interstate and wave, right? So how can we figure that out? Same idea as we did on our train, or our steamboats. It doesn't matter what you're driving. Same idea. Fill in your chart. I did the east and the west. So the east traveling is going a rate of 60, and the west is going 65. And it's a very similar to the last one, is that the time is the unknown. We're looking for time, and it's you left at the same time, heading towards each other. I think I said that in there. That you left at the same time. It should be inferred. Yeah, there it is, at the same time. So yes, the times are equal. And then the rate times time, we can put in the distance column, 60t and 65t. Then what to do with those? Well, how can we relate these two distances from what we know in the reading or what we know from our picture? So they will meet when this total distance is exactly covered between Ashland and Lexington, which is in the reading to be exactly 125 miles. Perfectly covered. So when is this distance, 60t, plus this distance equal exactly 125 miles? And then that is solvable. And again, I made this one up to solve out neatly, but they don't always. I should probably not always do that. But you get one. In exactly 1 hour, you're going to wave at your friends. So that's some pretty cool math to be aware of. And then there could be other scenarios. And this is just the idea of it. You could leave an hour later and have -1 there, or various scenarios with various rates, and figure this out and impress your friends. All right, another distance problem. Karen drove to her grandmother's house for a weekend visit. She averaged 40 miles per hour driving there on Friday. As she returned on Sunday, the traffic was lighter, so she was able to average 48 miles per hour, and her driving time was 1 hour less. Oh, we could have used that 1 hour less idea I've had in my mind to mix it up a bit. What is the distance between Karen's home and her grandmother? So again, if you want to draw that picture, we've got Karen, and she's going to grandmother's house, and then after the weekend, Karen is going back to Karen's house. So these distances to grandma's house and back home from grandma's house, and it didn't make as much effort there. We could have had a house and everything, right? But the distances, the idea is they're equal, right? A to and a from, the distances should be the same. So that'll give us a clue what to do when we get our distance box filled out. We'll set these distances equal this time. Just to kind of get a variety of things that could come up here. So what we know from our reading, the most obvious in this is the two rates. It's been a long, I think, so I like to fill those in first. The most obvious kind of builds some momentum. Then the times, they give us some sort of clue about time. In this scenario, the times aren't exactly the same. The way back, her time is 1 hour less because she's able to drive faster. So the distance is always rate times time, so that's 40t, and 48 times t minus 1. Not fitting that in there very well, but you get the ideas. These two times together. And then these distances are equal. You can see I've done that over here already for you. Set the two distances equal. Do our magic equation solving. You get t equals 6. So when time is 6. Now I want you to notice in this problem, the question is, so this sometimes happens, you got to be careful, and I'm the world's worst, so I'm not a good example. I'm trying real hard to be, though, right here. To look back. because on a multiple choice test, those meanies, they might have that as one of the choices, and that's not actually the final answer. The question is, what is the distance between Karen's home and her grandmother? So the question is about distance. We found out time, which is great, and that could be the question, but in 6 hours, that's 6 hours is how long it took her to go on the way to her grandma's house, which is a good thing to know. And then it would have been 5 hours on the way back. Great. But what's the distance? Distance is either 40 times t or 48 times t minus 1. We've got to put it into the distance part. So the first one's the easier one, 40 times t. So now we know t is 6. We know distance is 240 miles. Oh, Grandma lives a little ways away, doesn't she? But that is your final answer there, 240. All right, let's go ahead and start on the next type of problem, the mixture problem. The mixture problem, let me read this, make sure I get everything I wanted to say. For these problems, you will want to create a chart or think of this as 3 containers. A lot of these reading problems, like I said, use a chart. If you're looking at your book examples as well, you usually always see charts here. Or think about it as containers. That's kind of my way, and the book does that as well, both ways. You are mixing the contents of container 1 and container 2 to create a desired mixture. So here I've got a container plus a container to equal a container. I'm going to pour these into the final result bucket, so that's why it's addition. All right, so each container or beaker, if you were in maybe science class, will have an amount and a percent. The amount concentrated of whatever we're talking about, and then the amount concentrated, the percent I should mean, and then the amount, how much the capacity is. So it has 2 values in each container. The amount times the percent will give you how much of each substance is in each container. All right, so let's try this. Example 1. A pharmacist needs to create a 20% concentrated amoxicillin mixture. She has on hand a 15% concentrated as well as a 30% concentrated solution. How many ounces of the 15% should be added to 3 ounces of a 30% to obtain 20%? So amount percent plus amount percent equals amount percent. Now I know in the final result bucket this needs to be 20% concentrated. What I have on hand is a 15% and a 30% concentrated solution. And let's see, what does it say? She has on hand. Does it tell us how much in either one of these? It does. How many ounces? There's our basic unknown. How many for the 15? So there's my x. How many is the x of 15? Should be added to, there's the plus sign, 3 ounces is in this container to get my 20%. Now you'll notice I have a hanging percent here. Percent without an amount means nothing, so you can't leave a hanging percent. So what is this amount? It's not necessarily in that reading per se, but it is inferred. You're pouring these 2 amounts into this, so it's always these 2 amounts added together, x plus 3. And then you multiply, again, amount times percent. Multiply tells you how much you have in each bucket. So 15% or 0.15, because you have to move 2 left, times x plus 0.30 or 0.3 times 3 equals 0.2 or 0.20 times x plus 3. And then you'd solve that equation. To save time, I'm going to try to get your mixture problems in before my 15-minute YouTube time is up here. We'll see. Oh, I had that on the next page for you, didn't I? So I had that outlined as well. So explain further. And you get x equals 6. All right, moving on, I'm going to do another one. Same idea. It says how many liters of a 25% solution should be added to 5 liters of a 10 to get a 15. They're almost just laid out in order for you too, if you most of the time. I mean, I shouldn't say that, so you shouldn't count on that, but I was going to do my container idea. There's 3 containers. Okay, in the first container it says how many, so that's x of 25%. I'm going to add it to 5 liters of a 10% to get, there's my equal, or to obtain, same idea, 15%. Remember this hanging percent on the end. You have to remember these 2 amounts have to be added together there. So the formula is 0.25 times x plus 0.10 times 5 equals 0.15 of the two added together. All right, and it does look like I'm going to run out of time. I'll talk to you about 3 and 4 on the next video.